analysis, transfer function analysis, and AC analysis of this circuit. So that all was pre-layout simulation of this circuit. Today we are going to see post-layout simulation. So we will actually do the layout, we will do a layout for this same circuit. However, you can see that in this circuit we are having this current source that is generated by a reference generator circuit, and we cannot replace this current source in the layout by some equivalent. So what actually I am going to do before we embark on doing the layout, I am going to make little changes to make in this schematic, because we all know that we can use different types of biasing, though they have their advantages and disadvantages. Like in the previous session, for this common source amplifier, we used the current source biasing. But you will agree that we can also do a resistor biasing, means this current source can be replaced by an appropriate resistor, and we can get the same performance metrics even with by replacing this current source by an appropriate value of resistor. So first of all, we need to, because when we replace this current source by a resistor, we will be able to do the layout of a resistor. So that way we will also learn how to do the layout of a layout of passive component. Of course, we will be seeing only layout of this one passive component resistor. So let's see how we can replace this resistor. So see, if we can replace this current source by a resistor such that the current flowing in this branch is still 100 microampere and the voltage here at this node remains same as it is now. So that way we will be able to replace this current source by a resistor, right? And to find the value of that resistor, we can use the node voltage and the current. So current, we know that 100 microampere is the current. So let us first find this voltage of this node. And once we know the voltage at this node in this situation with this current source, using that voltage and this current, we can find the value of resistor that we shall use in place of this current source. So let me invoke simulation. So now we need to plot a voltage at this node net at 14. You see the current source, it is connected to net at 14. So let me plot the voltage at that node. So can I look? Yeah, we have this voltage net at 14 located over here. Okay, I think I shall zoom it, magnify, right? So what I'm saying that we can see that this current source is connected with net at 14 and ground. So we are going to plot this voltage at net at 14, so we can do it. So now we can see that this voltage is 1.8988 volt. So we can approximate it to be 1.9 volts. So now we can do what? We can go back to electric and we can see. So this voltage, you shall remember, it is 1.9 volt. So what we see that we have to connect a resistor here such that the voltage here is 1.9 volt and the current through this resistor is 100 microampere. So using this information, we can say that we shall connect a resistor of 19 kilo ohm in place of this current source. Do you agree? Do you agree? By knowing the voltage and the required current. So voltage here is 1.9 volt and the current that we want to flow through that resistor is 100 microampere. So using this voltage and current, we have found the value of resistor to be 19 kilo ohm. Do you have any doubt about that? Anybody having any doubt about that? I'm going to show you that actually by replacing this current source with appropriate value of resistor, still the circuit gives you the same functionality, same gain, everything. So nobody is saying, raising a doubt. So I think that you agree that we can replace this current source by 19 kilo ohm resistor. So now I'm going to delete this current source and I will go to components, and from here I will pick a resistor. So I have got multiple options for the resistor. I am going to choose Envel resistor because I have decided to use Envel resistor in the layout also. Although you have different options for the resistor in the layout also. So I have decided to use Envel resistor. You could have decided to use other resistors also. So I left click on this and this got attached. I bring it here. So now I will rotate it. So I go to edit and then I rotate it by 90 degree. Here it is. So now I will place it here and I will make connections by left click, right click, left click, right click. Now I shall change. Right now the default value of resistor is 100 kilo ohm. So I double click on this resistor and I can see that the value of this resistor here mentioned here is 100 kilo ohm only. So sorry, 100 ohm only. So I will replace it by 19K and then I click OK. So now I have connected a resistor of 19K in place of that current source. And let us very quickly, I will do only one analysis, DC analysis, so as to save upon time to do the layout. But through DC analysis, we can show that the behavior of this circuit remains same. The only difference is that in place of that current biasing, we are now connected a resistor. So I will save it and I will, okay, let me first exit from this stand. So I will go and invoke SPI simulation so we can plot V out. So this is V out that you can see we have plotted V out and it is going to very large value. So I will save it. So this is V out. Now let me plot a differential of this V out so that we can measure the gain. So minus V, right. So this is the gain, and now we can plot gain and see the gain at bias voltage. So bias voltage is 0.798. So let me bring that cursor. Here it is. So we can see that at 800. So you can see that you are getting a gain of 27. That is the gain that we got in the previous case also. So I hope you are convinced now that we can replace that current source by a resistor. Of course, the advantages of connecting a current source as a bias current, you all know that, and the disadvantages of having resistor. So you know that, but for today's session, this I have replaced this current source by this resistor so that we can do the layout of a resistor. Otherwise, current source, we cannot replace that current source by any equivalent in the layout. So that's it. Now we will go ahead and do the layout. So in this layout, we have two PMOS transistors of 10 micrometer width and one NMOS transistor of 10 micrometer width. So I'm assuming that this 10 micrometer width is a large width and we shall use a multi-finger transistor. So I have decided to use multi-finger transistors multi-finger transistor layout for these transistors. So let me go and create a layout view of this cell first. And I will also toggle the grid. So I will turn on the grid. Now I will go to, so I think I shall zoom it. So I will go to cell and new cell. In this new cell, I shall put exactly same name. So common source underscore amplifier, and this is a layout view. We are going to create a layout view. So I will select layout view and then I click OK. So now you can see that now you have got two views of this common source amplifier. Layout view is empty right now because we have not added any component to it. So now I'm going to add component to it. So you can go to component, but in the component you cannot find multi-finger transistors. So what we can do actually, we can go to tools, and in this tool you have a generation. So in generation we have an option for multi-finger transistor cell. So we will generate a multi-finger transistor from here. Now at this point you can select the technology. So we are working with MOSFET scalable CMOS, so it is there. Here you can select the type of the transistor. So I am going to generate a multi-finger PMOSFET first. So it is that already there. Uh, then we have this contact and then length of the transistor. So length of this transistor will be 2 lambda and width. So this width actually represents the width of the finger. So what I am going to do, the total width of the transistor is 50 lambda. So I am going to break that 50 lambda into 5 fingers of 10 lambda each. So I will make it 10, and then the number of fingers I will make it 5. So you have 5 fingers each of width 10 lambda, so that makes it 50 lambda wide. So click OK. So what happens, you have actually a new window opens up. I can even close this because that is already available. Oh, I lost it. I lost it. I will have to do it again. I will have to do. Yeah, it's there. So actually this zoom in and all is still window. So okay, let me, for a time being, I will have to stop this zoom. So you see that we have got this 5 fingers, 1, 2, 3, 4, and 5 fingers, and the width of this finger width. So right now the width of active region is referred to as finger width. So I will do what? It has been generated as a separate cell. So I will do what? I will copy it. I will select it like this, Control C, and I will go to this layout window, and here I can put Control V. So this got placed here. Now what I'm going to do, I am going to rotate it so that I have vertical polys, but you could have you can proceed with lateral poly also, but that is my personal choice that I would like the vertical polys in my layout. So I select it and I go to edit, rotate it by 90 degree. So I can also do a fill window so that you can clearly see. So right now we have generated this PMOSFET with 5 fingers, but we need to make proper connections. So for proper connections, first of all, what we need, that all these transistors, they are in parallel. Okay, so the gate of these transistors will be connected together. So how can I do that? So I will left click, right click, right click, right click, right click. So this way I have connected all the 5 gates together. Now we have learned the stick diagram of the parallel connected transistors. So we can actually say that, okay, this is drain of this transistor, then this is source of these two transistors. Then again, this is drain, this is source, this is drain, this is source, right? So what I am going to do now, I will bring I can do a connection like this. I can do a connection. So all sources that must be connected together. So I will do it like this. Left click, left click. So this is source, this is drain, this is also source. So I will select it and left click here. So now you can see that I have connected all the sources together. Similarly, and you can actually move it closer. There are scope of doing, but that is all optimization of the layout that takes time and is iterative process that you can do on your own. And when we are doing layout, we shall frequently run DRC. So you can invoke DRC from this tab or by pressing F5. So I will be pressing F5 for running DRC. This time I am clicking on it, and then we can see that there is no error there. So I can proceed. Now I have to connect the drain of all the transistors. So this is the drain, this is drain, this is drain. So I will do what? I will left click, uh, right click, right click, and right click. So here I have got this extended, so I will select it, and with an arrow key on the keyboard I can move it. So then what I need to do, and you can see that I am doing this layout for that transistor connected in diode connected transistor. So for diode connected transistor, we know that the drain of the PMOSFET and the gate of the transistor, that will be connected together. So we want to establish a connection between these two also. So how can I do that? For that, I can go to component, I can pick this poly to metal 1 contact, and I can actually put a poly to metal 1 contact here. Okay, let me first put it here. Yes, I can put it here also. And then first of all, let me make a connection with, okay, this is not done. So if you are if you struggle with the width of this polysilicon, so what I can do, I can select a pin here, then I can put a, okay, this pin here, I can put a pin here, and then I can connect it like this, and then I can move this pin here, and then I can again right click on this. So I have actually made a proper connection for this polysilicon. Then with an arrow key I can move it like this. Okay, let me, now I shall connect this with this. So metal, this got connected, and this is also connected with this metal. So I have connected this also. Let me run DRC. I am pressing F5, and I am fortunately I'm not getting any error. So zero errors and zero warnings. So with this I shall put it in full. So now we have actually drawn the layout of a PMOSFET configured as multi-finger transistor, and we have also made appropriate connections so as to configure it as diode connected, right? So now the next thing that I need to do is to set a SPICE model for these transistors, right? So I'm actually skipping some optimization options. Otherwise I could have done this like this, and I could have done this like, and I can actually delete it, so I can save upon some space here. I can save upon some space here, so I can also run it like this. I hope, yes, it's okay, no error. So I could also do it like this, no problem. Now I'm going to set a SPICE model for these transistors. So I will select this transistor, go to tools, then set a SPICE model, So when I set a SPICE model, something appeared here. Shall I magnify? So you can see that this SPICE model appeared here. Now I'm not able to select it by simply moving the mouse here. So what I can do, I will actually press the control button on my keyboard. Now when I click here, so I got selected, it got selected. Now I will double click on it, and now it becomes editable. So now I will write PMOS. Similarly, I will select this transistor. I will go to tools, SPICE simulation, set a SPICE model. So here also you can see, again I will have to press the control key, and then it got selected. Left click, leave the control button, double click on it and enter PMOS like that. Similarly, now I will select this transistor, go to tools, do the set SPICE model, and you can see that I will again press control key. This got selected, double click and then PMOS. And then again, I will have to do the same thing for these two transistors. So I am minimizing it and do it quickly because I have already shown you how to do that. So I will select this transistor, go to tools, SPICE simulation, set a SPICE model, press the control key, bring your mouse here, it got selected. Leave the control button, double click on it, now edit it, PMOS. Similarly, the last one. Now this tool, set a SPICE model, press the control button, bring your mouse here, got selected, double click, PMOS. Right. So now the layout of this PMOSFET is complete. Now, since the other PMOSFET that we have to use in this circuit has the same size, same length and width, only the connection is different. So what I can do actually, I can copy this same layout and I can make certain changes like there the input and the drain is not connected together. So that changes I will make. So what I am going to do, I am going to copy this by selecting it like this. I will press Ctrl C and then I will go there. I will click my mouse here and Ctrl V. So this thing you can see that this got placed here, but I shall actually move it. So I can do Control 0. So I can just place it here. So I placed another PMOSFET and window, fill window. So I have placed another PMOSFET which has to be which is of the same size. Certain changes are to be made from connection point of view. So I am going to do those changes, but before that what I can do actually, I can bring it a little closer and align the two transistors so that the layout looks good. So that's it. I press the F5 button to check DRC, so no zero errors, zero warnings. So that's good. Now we are going to make the changes because for the other PMOSFET, the gate and drain is not connected together. So I will press delete. I will press a left button of the mouse here and then press delete key on my keyboard. So I am able to delete that. And then I will also delete this thing from here. So now you can see that I have here, let me clean it. So now you can see, now we have to connect these together. So this is drain, and this shall be connected to this. So let me hit the F5 button again. No errors, that's fine. Now for this transistor, this gate. So if we go to the schematic, so you can see that the gate of the two PMOSFET, they are connected together, right? So let's go to layout. So what actually we need to connect this and this polysilicon together. So I will left click here and I will right click here. The two poly got connected together. So I hit the F5 button again. That's good. Zero error, zero warning. So this way I have completed the layout of multi-finger PMOSFET. Right. Let's go ahead and do the layout of multi-finger NMOSFET, that is driver in our circuit. So I will go again to the tools and then I will go to generation and okay, let me magnify it. So now I have to do the layout of multi-finger NMOSFET. So I go to tools and then I go to generation, and in generation I have this option of multi-finger transistor. So this window pops up. So now I will select it and I will make it N transistor, and this length remains same 2 lambda. Width of the finger, so that is 10 lambda. So this green region you are seeing now from here to here, that is the width of the finger. And then we have 5 fingers because the size of the N MOSFET is also same as this P MOSFET. So I hit OK. So we got this. So what I can do, I can actually minimize it. So at this point of time, I will have to minimize this window actually. Okay, now you see that NMOS has been created here. So I will again select it from here by the help of mouse. I got it selected, then I can copy it by pressing Ctrl C. Got copied, then I will go to the layout window. Now I will first minimize this window by pressing Ctrl 0. So I can minimize it and create some space. And now I press Ctrl V. So this got placed here. Now I need to rotate it. So I will go to edit, rotate by 90 degree. So this is got rotated, right? So now this P MOSFET, we have, sorry, this N MOSFET. Now we have to work on this N MOSFET. So I will do what? I will maximize now this window by pressing Control and 7, key 7. So I can maximize, then I can align it. So this is N MOSFET where I need to make the appropriate connections. So first of all, I need to connect the gate of all the 5 transistors. So left click, right click, right click, right click, right click. So this way I have connected all the 5 fingers together, and then I can set a SPICE model. Okay, let us set a SPICE model first. So I go to simulation, SPICE, set a SPICE model. Then I press Control button, bring my mouse here, click, so it got selected. Double click, it becomes editable. Then I enter the model name. Similarly, I select this finger, I go to Tools, Simulation, Spice. Under that, we have set a Spice model. Now again, I press the Control button and bring my mouse here. So got selected, double click on it. So this got editable. Similarly, I repeat this process. So let me repeat it. Control, double click, and mouse. So actually what I am doing the same thing repeatedly. So you can say this is the disadvantage, or this is advantages associated with freely available tools. Means you cannot have all the features available in commercial tools, but that's fine. We can at least learn layout using this freely available tool. So again, I go to this set spice model control, and at least the size of the circuits that we will be dealing with. So those circuits will not be that much large that these things pose a big challenge. So that can be managed actually. Now in this transistor, what we are going to do, let me say that this is a source. So this becomes drain. This is source, this becomes drain. This is source, this becomes drain. So I'm going to do what? I'm going to connect all the drains together first. So I will connect all the drains together. Okay, let me see what I have done here. So I have connected, okay, so if I want to align the source drain like this, so that way we can do it, otherwise no issue, we can do that also. So left click, right click, right click, right click. And then what I can do actually, this is source, this is drain, so this is source, this is drain, so this drain. So now I have connected the drain of all the 5 transistors, 5 fingers together. Similarly, I have to connect the source of all the 5 transistors together. So I will left click, right click, right click, right click. So here I have got a pin that is extending beyond, so I can connect that. And this is also source. So left click, right click. So this way I have connected. So let me do a fill window so that we can see all the 3 together. Now what I can do actually, I can place this NMOSFET, I can place this NMOSFET close to this PMOSFET, and when we have to place it, I can move after selecting it. I am moving it up and down by using the arrow key on my keyboard, so that I can able to. Now you see that this is the drain terminal of this PMOSFET, and this is the drain terminal of NMOSFET, and they have to be connected together because the drain of the PMOSFET and drain of this NMOSFET is to be connected together. This we have already seen from the configuration, circuit configuration. So what I can do actually, this I think this is not needed, so I will delete it. This is not needed, I will delete it. Now we can see that we can actually bring this like this: left click, right click, left click, right click, right click. So now you can see that we have connected the drain of this NMOSFET and drain of PMOSFET together. And let me run a DRC. So I am hitting F5 button. That's good. No error, zero errors, zero warnings. So by this time, we have created the layout of the 2 P MOSFET and the 1 N MOSFET in our circuit, right? So, and of course, certain optimizations that are possible. So I am not paying attention to that. For example, you can bring the 2 transistors closer, but that you can do, no issue. I'm leaving it because that optimization that takes time and it comes with experience. So now the last component that is left is resistor. So here we have to learn something new actually. So what you see that I will go to components, and after that actually we can delete these cells actually. So I will select it and then I will do the delete. So now go to components. Now in this component you have the resistor option here. Okay, let me magnify it. In the components, when you go to components, so you have the resistor options here. You have multiple options for the resistor actually. You can see this. You have multiple options for the resistor, right? You can have an P-active resistor. You can have a high resistor poly 2. You can have an active, N-well, P-well, N-well. So different kind of resistors are available. Since I have decided to use Envel resistor, so I am going to select this Envel resistor, right? So I will click on this Envel resistor. But before that, let me tell you one thing. Tell you one thing. So what happens? This Envel resistor will use an Envel as a resistor, and sheet resistance will govern the value of the resistance, right? So I need to do a few settings first. So you see from the schematic, we know that we need a 19 kilo ohm resistor, and for this passive component for this resistor, actually, when we go to files, preferences, and in these preferences, I go to tools, then parasitics. So here you can see that you have different layers, and sheet resistance and the associated capacitances are listed over here. So actually I am interested in Nvel, so I will select Nvel. and by default the resistance of Envel is 0 here, right? So we have to actually enter appropriate value of sheet resistance for Envel. So where shall we find the value of this Envel sheet resistance? So I have actually found it from the technology file. I will show you where it is there in the technology file. But the value, let me enter the value. It is 1005, right? So that is the value of sheet resistance for Envel. So I have entered. So this is again, you can say, is a manual process that we are doing because we are working with a free available tool. When you will be working with commercial tools like Cadence and all, so when you bind a PDK with your project, so all these information will actually be embedded into that. But since we are working with a free available tool, so we need to do some settings manually. So, but this value, I am not entering arbitrary value. This value is from the foundry reported value for 350 nanometer technology. I will show you that file. But I have entered this value. So now the sheet resistance is 1000, nearly 1 kilo ohm, you can say. And I'm not adding these values, although these values are also there in the technology file. So apply and okay. So mark all libraries. So that's it. Let me minimize it, this window, and let me go to that file that I'm talking about. So that technology file comes with Moses 350, and so that actually comes with the means that file is released by the foundry. So here we have Moses file TSMC 0.35 micron. So when I open this file, let me maximize it. So when I open this file, you can see that this file actually reports certain technology values. So you can see that vendor is TSMC, feature size 0.35 micron. Okay. So here you can see certain parameters related to the transistor width and length and then all. So, and then you have this process uh, parameter like mu Cox by 2. Then you have the low field mobility. Anyway, we are interested in the this thing. We are interested in sheet resistance. Here you can see. So you have the sheet resistance, contact resistance, and gate oxide resistance, and you have N plus active. So N plus active sheet resistance here you can see is 3.3 ohm per square. You have the unit here, ohm per square. Okay, and, this is about the active regions we have here. The well is here. So you can see that the sheet resistance of Envel. So under Envel, you can see that it is 1005 ohms per square. So this file is actually released by the foundry, which has got certain technology information. So you have all those informations like the capacitances, you can see that capacitances per unit area. So all that information, technology related information is there in this file. So anyway, I wanted to show that the value of the sheet resistance that I entered there in electric is not an arbitrary value that I have chosen. Rather, that value is reported by the foundry. So this is the file reported by TSMC file. Fine. Okay, so let me minimize it. So and close this. So that is where we found that value. Now let us again go back to electric. Now you see, we have to realize a 19 kilo ohm resistor. So I'm going to this Envel and Envel resistor, and I will select Envel resistor. Where is Envel resistor? Envel resistor, right? So when I bring that Envel resistor here, I get this thing. You see, when I brought that Envel resistor, I got this thing. So you have an Envel, and then you have a well to metal contact here, well to metal contact here, right? Now you see, the default or the design rule dictates that the minimum width of this Envel. So what shall be the minimum width of Envel? So by default here it is so you can actually select and double click to change the properties of this. So you can see that I'm double clicking, so this thing opens up. So you can see that the default width is 12 lambda, and the right now the length is 41 lambda. So now you can see that sheet resistance is 1000, right? So sheet resistance is 1000, and we have to realize a resistor of 19 kilo ohm. So what it means that you have 1 kilo ohm resistance per square, right? So for 19 kilo ohm, you need 19 squares. Shall I do it on? Let me presentation. Yes. Okay. So you see, we have to realize a resistance of 19 kilo ohm. I hope that my screen is visible. Is my screen visible? I am writing something. Can somebody
Yes, it is. Yes, it is.
12 lambda on this side, 1 square means resistance. This resistance will be actually
1 kilo.
1 kilo ohm. So from here, to get a 19 kilo ohm resistor, we can calculate the lateral extension of this. So we can multiply 12 by 19. So that comes out to be 228 lambda. So what we get from here, that this resistor, Envel resistor, shall be 220 lambda long. So if we do a 220 lambda long Envel, that will actually make this layout very asymmetric. Means you will have a very long Envel. So what actually we can do? We can connect multiple Envels like this. So let me go back. So what actually can do? We can have these resistors like this. We can have these resistors, means of bring it closer, because the spacing required between two N wells is minimum 6 lambda, so that I will be able to satisfy with this much spacing. So I am moving it with the help of arrow key on my keyboard. So I bring my mouse here, I left click, release the mouse button, then I press the arrow key on my keyboard, so to align it. So I have done it, so fine. So now I will minimize actually and run the VRC. So I'm hitting F5. So that's good. No errors, zero warning. Fine. So now we have placed. Now you can actually see why in the design, in the circuit design, particularly analog circuit design, we have been taught to avoid using passive components in our circuit, right? You can see that 3 of our transistors that is consuming uh, relatively a smaller area as compared to the area consumed by this one resistor of 19 kilo ohm. So that is why we have been taught in analog design principles that we shall avoid the use of passive components, because passive components, they consume, and large value passive components, they consume large area on an IC. So I hope I have made this point clear. Now I have to make connections. So how shall I make that connection? Okay, so I will make connections between these nodes. So let me go here. I will make a connection. Left click, right click, left click, right click, left click, right click. And then this terminal of the resistor is to be connected to the diode connected transistor. So I left click here, right click here. I have connected it. Let me hit the F5 button, so that, okay, so zero errors. I just did the DRC, 0 errors, 0 warnings. So now what is left? I need to connect this terminal of the resistor and this source of NMOSFET, and that will actually be grounded. So I do what? I left click here, I right click here, and then I right click here. So I have made that connection. I will do a little, uh, not that, no, not, okay, leave it. So let me minimize it and hit the F5 button again. So that's good. 0 errors, 0 warnings. So I have done the layout of 3 transistors and one resistor of 19 kilo ohm. Okay, after that, okay, what is left now? Okay, uh, yes, I shall do one. I shall do one more thing. That, right, I shall do a well connection also with these transistors. I have not yet placed wells, so I will maximize it. So I have not put the well contact for the P MOSFET and for the N MOSFET. So we know that the source of the N MOSFET and the well will be grounded. So now I go and select P well, because this NMOS is housed in P well. So I put a P well here, and then what I do, I will uh, I'll, edit the size of this P well. So let me edit it. So let me make it 15 lambda wide and 6 lambda, 6 lambda. Okay. So this is the well. Now you know that I can bring this well closer. So for that I shall create a space here first. I shall create a space here. So what I need to do, I can bring this well here too close, I think.
Sir, is it a dual well process?
Pardon?
Is it a dual well
Yes.
process?
Uh,
Acha, okay. Okay.
yes, ma'am. Yes,
Okay,
ma'am.
okay. Uh-huh.
P MOSFET, they are placed in Envel, and N MOSFET are placed in P well.
Okay, okay.
So let me just, okay. So now I can do the connections like this. So this is source, this is well, this is source, this is well. Right click, right click. So I have made the well contact for this N MOSFET. Let me hit the F5. Okay, good. No error. Now I also need to put a well for P MOSFET. So I will go and select N well and bring it here. And let me adjust the size of this N well, so that will extend actually 10, 20, 30, 40, 70, 80, 90, 100, 110, 120. So I can make it actually 120 lambda wide and this 6 lambda. Okay, so that's it. Now I have to, so I will do a little editing here again. So I can actually directly connect, bring this well closer, and I can actually connect this like this. Left click, right click, left click, right click. So now, so this is the VDD line actually. So let me hit the F5 button again. Oh, I got too many errors. Now, let me see. So I am pressing Shift button and greater than a smaller than button. So it is showing that I have placed it closer. So you can see that it is reporting that metal 1 N well contact less than 6 lambda. So what it means that I need to move it farther. Let me hit the F5 button again. So it's again showing that Okay, let me move it farther. So let me move it here. So now I'm pressing F. Now I'm not. I pressed F5 button again, and now that has been solved. So although I just moved it farther, I have not optimized it. So you can do that optimization, no issue. So now I have to. I think this layout is complete. Let me do fill window so that I can see all the components together. So this is the layout, not very optimized. I accept that, but we have multi-finger. We have used multi-finger transistors for P MOSFET and for N MOSFET, and we have used Envel for the resistor. Now it's time to create or export these ports. So I go here, select left click on it, and then I go to export, create export, and this is VDD. So I select here power. Okay, so that VDD I got. So if it is not visible, I shall make it larger. So I will go to edit properties, object properties, points. So I can make it 15. I can make it even greater. Right. Now we can clearly see this VDD port. Similarly, I have to export ground. So I select this pin. I go to export, create export, GND, and this is ground. So now this is again of very small size. So I press Control button and try to select this. So by pressing my mouse multiple times, I am able to select it. Then I go to object properties and make it 20, apply. Okay. So now we can see that we have created two ports, VDD and ground. Now we have to create export two more ports. One is input and another is output. So I am zooming in. So I am pressing Control and then 7. Control 7 will actually zoom. So you see we have to apply input. This is the gate where we have to apply input. So to create an input port, what I'm going to do, I will use a poly to metal contact. Suppose I put my input here. So that's it. Left click, right click, right click. Oh no. Left click, right click. So whenever you have this kind of problem, so what we shall do actually, we shall go and select a poly pin from here. This is poly pin. So what we can do actually, we can put poly pin in between, and then we can actually, then we can run this, and then we can run this. No, Control Z. Okay, this is happening. Why it is happening? Let me do some alignments. Left click, right click. Okay, I got it. So let me hit the DRC F5 button. So fortunately, zero errors, zero warnings. So this is an input. This is the input port where we will be applying input. So I select this. I go to export, create export, and then V in is that. So that is input. So okay, that's input. We have the input port in place. Then we are left with the output. So you can see that this is the drain terminal of this P MOSFET load and N MOSFET driver. So this is the output port. So select this pin and go to export, create export, V out, and then output. Okay. So I have created the ports. Now I will fit in, so fill in. So at this point, I have created all the ports. Now I need to add a SPICE code to it. So SPICE code, we need to add a SPICE code to it. So I can do what? I can directly go to schematic and I can copy this SPICE code by when I bring my mouse here, it gets highlighted. I left click and release the mouse button. It got selected. Then I do Control C and then I go to the layout and here I click my mouse here and then I do Control V. Now, right now, this size of this text is very small. So what we can do actually, we can go to Edit, Properties, Object Properties, and from here we can actually do it, adjust the size. So I make it 20 and I can actually see by apply. So now it is okay. So I hit OK. So this is it. So this layout we have done, and this layout is DRC clean. No DRC is there, right? Now I shall go to Weld check. So Weld check gives me an error. So let me see what that error is. Shift. So that error is no Envel contact. No Envel contact in this area. Okay, we are using this multi-finger transistor. What could be Envel contact? Yeah. Or there some other error? Why it is giving no Envel contact in the area we have made those contacts? Uh, this is metal 1 Envel contact, and we have all these contacts. So actually, this thing what we can do actually this resistor is also going to give that kind of error because this well is also means this is N well and we have not connected this well. So what we can actually do, we can go to file, preferences, and in this preferences in well check, okay, must be connected to power, must have contact in every area. For P wells, must connect to ground, that we have done. So this is okay. Going wrong, it is giving. Okay, let me zoom in. Let's see why this is error is there. Okay, this is the why this error is there. These are all connected. All connected. F5 button again. Okay. So let me do the well check again. Okay, no well errors. So now you see, I have got no well errors. So actually, I have not placed that well. I have not placed appropriately. That's why I was getting that error. So in the meantime, this happens when you zoom in and zoom out your window. These texts actually get merged, but that is not going to affect your simulation. And if you want to edit this text, you can always go and double click here. When you double click here, you will be able to see these texts correctly. So that is not going to cause any error in the simulation. So we
Uh,
have done the pardon.
excuse me, sir.
Yes.
So there is no problem of putting the well after PMOS, NMOS transistors are placed, because generally it is the start. You start with a material, that is silicon material, then have these two wells and then embed these transistors in that. Now we have placed the wells after we place the transistor, so there is no problem.
No, while doing that layout, it is no problem.
Acha, okay.
Actually, the P MOSFET that we picked from the component, so
Uh,
that is already placed in P well.
uh,
So after that, this is actually is the P well contact.
yeah, but without defining the wells, we place the transistor first and then we place the wells. So there is no problem. Yes,
Actually,
sir.
let me zoom it out, ma'am. Let
Hmm.
me zoom it out, and I will show you that what is happened. See the P MOSFET that we have put, so that was already in Envel, and after that we bring this well contact.
Hmm.
So that well contact is also in Envel. So
Okay.
we have actually merged the two wells. Can you
Mm-hmm.
please see it? Is it visible?
Merge the two wells means well of the resistor and well of the PMOS
No,
transistors.
not the resistor. Let me invert the colors maybe. Right now. Now I think it will be visible more clearly. So
Hmm.
this is actually P well, N well, sorry, N well for P MOSFET. We have placed
Correct.
this P MOSFET.
Uh-huh.
This hash, yellow hash is actually P select, and
Uh.
then we have this N well,
Okay.
this N
Yes.
well. So here we have this N well, and this is N select because for doing well contact we
Mm-hmm.
dope with N plus region. So
Yes,
this is
correct.
N select region.
Okay.
This is N
Okay.
select region and this is N well. So
Okay.
now you can see that this well contact, well contact and well of P MOSFET we have merged together.
Uh-huh. Okay. Okay.
So now we can say that this P MOSFET and this well contact, all that is part of one well.
Okay, sir. Okay.
That
Okay. Yeah. Previously, it was not seen. Wells were not seen properly.
yes, ma'am. Actually, this
Hmm.
is free tool, so we need to
Yeah.
apply
Yeah.
some
That
tricks,
I agree. That I agree, sir. I agree.
tricks to do these things. So okay, let me. So now now actually I shall invert the color again. Uh, so color scheme, for color, right? Now there is one challenge with this free tool that I am facing, that when I go and do the NCC, so when I do the NCC, it reports me some error, and that error is on the part of the components, resistor Envel. What it reports that in a schematic, I have only one component of resistor, and in layout, I am having four components. So I have been facing this challenge, and because of that, we cannot do away with this NCC error. But that is not going to affect the simulation or the functionality of this circuit that we are going to analyze. So for that, I will be sorry to not have the solution at this point of time how to solve this error, because in a schematic we have used only one resistor, uh, this resistor, and in layout we have actually four components, so it is actually considering these four components separately. So at this point of time I do not have answer to that problem, but that is not going to affect the functionality of the circuit. Now we are ready to go ahead with the simulation and analysis of this circuit, right? So from the previous session, we know that the gain of this circuit was around 27. So
Hello,
we
sir.
are now, pardon?
Hello, sir.
Yes,
In
pardon.
schematic, hello.
Yes, please.
In schematic, can we go for having 4.75 kilo ohms? Of,
Yes, ma'am. Your suggestion is good, and actually, I tried that also. Unfortunately, I was not able to solve that problem. I tried that
uh,
solution that you are suggesting.
okay,
I
sir.
tried that. I connected four resistors here of
Uh-huh,
4.75 kilo ohm.
uh-huh.
So, but I was not able to solve that problem. So,
Okay, sir.
sorry for that.
Okay, sir. No problem.
So, let us go and do the analysis of this layout. So, first of all, we will do the DC analysis. So, we already have the command for DC analysis in place. So, I go and invoke. Okay, let me first close this instance of LTS Spice. So I exit from that instance of LTS Spice, and then I go and invoke SPICE simulation from this tool. So I go to simulation, write SPICE deck, and now you can see the netlist generated. So let me first show you the netlist that has been generated from this layout. So you can see now you have 4 NMOSFETs connected in parallel, and the width of the NMOSFET, each NMOSFET is 2 micrometer. So the total width becomes 10 micrometer. Similarly, we have this 4P MOSFET, 5P MOSFET, sorry. So 2 micrometer each. So that makes it 10 micrometer, and then we have another P MOSFET, 5 P MOSFETs connected in parallel, and then we have 2 micrometer finger width. So that makes it 10 micrometer. So this is how the netlist is extracted from the layout. Similarly, we have 4 resistors extracted from the layout, and then we have a whole list of parasitic capacitances. We have extracted parasitic capacitances, then we have list of extracted parasitic resistances. So this is what we mean by parasitic extraction, and this is a long file, and then we have our SPICE code that we have entered, right? So this is the netlist, how it looks after we do it from layout, after we extract it from layout, and you can see the difference between the netlist extracted from schematic and netlist extracted from layout. So when we extract this netlist from layout, we have all sort of parasitics appended to the netlist. Now let us go and see the performance. So first of all, I am going to plot V out. So now what will happen, actually, it has got so many nodes. So this is actually difficult to select that or I locate that node. So what I can do, I can search that node from this. Okay, let me maximize it. So here you have large number of nodes because this netlist has been extracted from the parameter along with parasitics. So I know that I want to plot V out. So this is actually kind of search. So when I put out, so that V out will be listed here. So I click here. Now I have got that V out. Now let me fit in this. So I have got this V out. And this is actually going to 1.5 volt because in our DC analysis, I have swept V in from 0.6 to 1.5 volt. That's okay, no issue. Now I am going to do a differential of it so that we can measure the gain from here. So I do minus D V out and hit this. So this is the plot. Now I bring my cursor here and input. So bias is 0.798. So I set the bias 0.798. Yeah, here. So now you can see that you are getting this gain of, you can see that with that bias voltage of 0.798, we are getting that same gain. We got there also 27, around 27. Here also you are getting 26.5. So what is the take from here? That we can actually, we are getting similar or identical DC performance. Now I want to plot this V out gain versus V out. So what I can do, I can bring my mouse here and right click here, and then I can select that I want to plot V out. So V out, right? Okay, so you got that same kind of plot that we saw in the last session again. So you can see that the gain remains almost constant in this region when the V out is 0.9 to say 1.5 volt. This is the region. So using these plots, actually, we can identify the signal swing at the output without losing the gain. So that was the DC analysis. Now let us go ahead and do the other analysis. So I will exit from this. I will go here and modify the code for transient analysis. Let's go and do the transient analysis first. So I modify the code here for transient analysis, and then I do it, and I do transient analysis for 2 milliseconds. That's it. right? So I go and again invoke SPICE simulation. So now I want to plot V out. So again I can search from here out. So this is V out, and if you want to plot V in, so I can add another plot pane, and here I can plot. So again I can search with the help of V in. Oh, what happened? I'm not able to select. Okay, this V in is there. So now you can see that we have got both V out and V in. So V in, we know that the input signal swing is 20 millivolt peak to peak because we have applied that signal. Let us try to measure the gain from transient analysis also. So I bring my mouse here and I left click. So one cursor got attached. I bring my mouse here, again left click, second cursor got attached. I set these cursors at the peak values, and then we can read the delta. So the delta here is 519.86. So if I divide 519.86 divided by 20 millivolts, so this comes out to be 25.99. So again, we are getting the gain that we designed this circuit for, right? So that was the transient analysis. Now again, I skip this LTS spice instant, and this has corrected automatically. You can see some magic has happened. So now we go again, and now we do transfer function analysis. So I go here, I left click, and I do a transfer function analysis. Right? So now I go and invoke the simulation again, write SPICE tech. So I can see that this transfer function analysis gives me a gain of 26.4. You can see this. So the transfer function result is also similar to what we expected. Let me see. Am I able? So this is transfer function analysis. Now we shall go and do the AC analysis, where we will see the difference between the pre-layout simulation and post-layout simulation. Because in AC analysis, what will happen? All those parasitic capacitances that have been extracted from the layout, they come into picture in AC analysis. So in AC analysis, all those parasitic capacitances, they will come into picture, they play a role. So what we do, let me go and do the AC analysis and see the behavior of the circuit. So I go and do the AC analysis, and I do AC analysis from say 1 kilohertz to 100 gigahertz for this circuit. Now I go and hit the simulation, write SPICE deck. So what happened? Okay, I forgot to comment the .tf analysis. I should have commented because transfer function analysis and AC analysis cannot go together. So I forgot to comment that. So now I have made that correction. Now I shall go and invoke the SPICE simulation from here. And now we have this plot. So now we need to plot that V out. So I will select out, V out. Now you can see that from this AC analysis, we can see the unity gain bandwidth. Let us measure the unity gain bandwidth for this circuit. So the unity gain bandwidth from post layout simulation is around. So we can see, you can see the unity gain bandwidth from the post layout simulation is 4.13 gigahertz. 4.13 gigahertz is the unity gain bandwidth from post layout simulation. And if you remember, from the pre layout simulation, we had got this unity gain bandwidth much larger than the post layout simulation. So we can actually verify that. So I am noting down this value, the value that we got here. So 4.13 gigahertz. 4.13 gigahertz is the unity gain bandwidth of this common source amplifier that we are getting from post layout simulation. So let us go and do the pre-layout simulation also, and let us again measure the unity gain bandwidth from pre-layout simulation. So I will comment this DC analysis and I will do AC analysis, but I remember that we were not able to get the unity gain bandwidth by doing 100 gigahertz, so I am making it 1000 gigahertz. Means I am just increasing the frequency range, nothing more. Right. Now I invoke the simulation from here, that is pre-layout simulation I am invoking. So write a SPICE deck and then plot V out. So here we are. So you can see even for 1 terahertz, we are not going to that 0 dB gain. So you can, do you see that? So even for 1 terahertz, we are not going below 6 dB. Means you can say that the unity gain bandwidth from this pre-layout simulation is much larger than the unity gain bandwidth that we got from post layout simulation. And I shall, at this point of time, I shall tell you that the results that we get from post layout simulation is more realistic, because this post layout simulation takes into account all the parasitics that will be existing on the silicon. When you put your circuit on the piece of silicon, so all the parasitics and the parasitic capacitances and resistances associated with all these metal lines, poly lines that you are running, so all that will come into picture. Whereas when we are doing a schematic, so we are only taking into account the properties of these devices. These arcs, the connecting wires, they are not offering any resistance, or they are not associated, they are not having any capacitance associated in this schematic. So this schematic actually uses only the device properties, and that is why you can see the schematic, the netlist extracted, the netlist that is extracted from the schematic. So it is having only the components, right? And these components, they are calling the model. So only the device properties will be taken into account. Even the area and perimeter of source and drain, they are not there. So what it means, that the capacitances associated with the source and drain of the transistors, they will not be taken into account in pre-layout simulation. So that is why pre-layout simulation, the results that you get, particularly the results of the AC analysis, so the results that you get from pre-layout simulation will be off from the results that you get from post layout simulation. And that is why you see, when you see the analog design flow, so after doing post layout simulation, it is indicated that if you are not meeting the specification, you go back and either do some changes in the layout or do some changes in the schematic. So that is what is the iterative process. So analog design, it is actually a iterative process. You will never pass or meet the constraints in one pass. For example, I have done only one pass. I did the schematic, I did the layout. So that is one pass. So I'm not meeting the schematic, that I'm not meeting the specification. And that specification may be from the performance point of view or from the area point of view also. So I will have to redo or make changes in the layout or make changes in the schematic to meet those specifications, right? So that is what I had for this uh, layout thing. And after this layout thing, I will quickly, in 2-3 slides, I would like to highlight the reason of using multi-finger transistors. Many of you may be aware of that thing, but for the completion of this discussion, I would like to go through 2-3 slides that actually highlights the importance of using multi-finger transistors. So what happens? Rathod sir, can you confirm that my slide is visible?
Yes, sir. Yes, visible.
Thank you. So see, if we have to do the layout of a wide transistor, for example, in our circuit, we had the transistor as wide as 10 micrometer, but that is not a very wide transistor. You may have to lay out a transistor having width of 100 micrometer also in analog design. So that is not unusual. In analog design, you may have to do the layout of a transistor that is having a width of 100 micrometer. So what happens if you are using a single finger transistor? So what here we are seeing that we are having a single finger transistor and we are also having single contact, right? Now these are the points that we shall take into account. For example, these numbers here has been taken for 0.18 micron CMOS process, that the gate series resistance. So you are applying signal to the gate at this point, and this signal has to travel from this point to this point. So this polysilicon gate that has got a finite resistance, and that resistance is of the order of 7.8 ohms per square. That is a sheet resistance. So what will happen actually, and this polysilicon gate has capacitances associated with it. So that will actually delay the signal. So signal will reach here first and reach here last. So the transistor region or the channel will form here first and form here last. So whole of the transistor will not be turned on simultaneously, right? Another point is that you have large distributed resistance of source drain. So you are applying signal or voltage here only. So when the current has to flow, so the current is flowing in this region, that will experience a smaller resistance as compared to the current going through this region. So when the current going through this region, that will experience a larger resistance, right? And similarly, you have large source drain and resistance and parasitic capacitances. So area of the source and drain, that will govern the parasitic capacitances associated with source and drain. So that same thing has been highlighted here, that the current flow is non-uniform when you are using a contact only here and using a long polysilicon gate. So these series resistances, they come into picture, and the current density in this region will be larger and current density here will be smaller. So the current flow will not be uniform all along the width of the transistor, and this can actually be considered as a parallel transistor. So this one transistor can be broken down into multiple transistors, and this can be considered like these parallel transistors connected like this, and you have these resistances like this. Okay, so that is actually unwanted. These resistances, they are unwanted. So what are the main issues in laying out wide transistors? So parasitic resistance at source and drain must be kept as low as possible. That is one goal. Then the gate resistance must be minimized. That is, the series resistance slows down switching speed, because whole of the transistor will not switch simultaneously. And then the parasitic source substrate and drain substrate capacitances must be minimized. So these are the issues that shall be taken into account while laying out wide transistors. Therefore, we shall have these three important goals in our mind while doing the layout of wide transistors, that we have to minimize the source drain resistance. So, and we have to minimize the source substrate and drain substrate parasitic capacitances. And lastly, we have to minimize gate series resistance. So these are the three primary goals that we shall take into account, keep in our mind while laying out transistors. So let us see how we can meet these goals. So for minimizing source drain contact resistance, we can actually put multiple contacts all over the active region. So what you see over here, you have placed multiple contacts all over the active region. So now you are applying signal to the drain of the transistor using this metal line and using these contacts simultaneously. So you can see that these resistances now they are connected in parallel. So all the resistances connected with these contacts, they appear in parallel, and therefore the overall resistance has reduced. And current is uniformly spread. So now the current distribution all over the width of the transistor. So this is the width of the transistor. So all over the width of the transistor, the current distribution will be uniform and the source drain resistance will be small. So this is how we can actually address that first goal of minimizing the source drain contact resistance. Let us go and see how we can address the second goal or achieve the second goal. So for minimizing gate resistance, what we can do, rather than feeding the signal from one side only, we can feed signal from both sides. So that is what you see. This is the signal, input signal. So rather than feeding input signal from one side only, you are feeding input signal from both the sides, right? So this is one way of minimizing the effect of gate resistance, because now you are feeding the signal from both the sides. That same thing could have been done in our case also. We could have actually joined these poly gate ends also. These poly gate ends also we could have joined, right? And that is often done. Okay. So this is one approach, but even when you are feeding signal from both the sides, still if the transistor size or transistor is very wide, you will not be able to minimize the gate resistance. So there is another possibility of using multi-finger transistors that we have done in this session, that you can actually break that one single finger transistor into multi-finger transistor. So now you have a smaller segment of polysilicon gates, and therefore that issue of a large series resistance gate can be addressed, right? So for example, here you can see you have broken down that single polysilicon gate into 4 segments. So you have 4 transistors connected in parallel. So you see 4 transistors connected in parallel. Now multi-finger layout with shared source drain. So here you see 4 transistors connected in parallel, but the source drain, they are not shared. So actually they may result into increase in the area, source drain area. So what you can do, actually you can merge the source drain, you can share the source drain of the transistors, and by sharing the source drain of the transistors, you will be able to minimize the source drain area of the transistor. For example, here we have 4 transistors. Okay, now you can see that now you have only 3 sources. So 1, 2, 3. So actually in single finger transistor, if the width of the transistor was W, okay, so means you have broken down into W by 4. So W by 4, and then you have 3 source regions. So this will become 3 by 4. So that is what you see, that the with this multi-fingered shared source drain transistor, you have actually reduced the capacitance. Initial capacitance associated with source is CS dash, and now that has reduced to 3/4 of that value. So using multi-finger transistor with shared source drain not only addresses the issue of large series gate resistance, but it also reduces the parasitic capacitances associated with source drain. Similarly, you can see that you have only 2 drain regions here, right? So effectively, you have made the area of the drain half than the transistor, single finger transistor. So that is why the parasitic capacitance associated with drain in this layout is half of the parasitic capacitance associated with drain in the original single finger layout. So I think this is what I wanted to say about the multi-finger transistor layout and the motivation behind doing the multi-finger transistor layout for wide transistors. So that's what I had for this session. Now, if you have any query, I will try to answer your queries if I can. So it is very quiet, I think, as if nobody is having any query.
Any queries?
I'm not able to hear. Is anybody asking for some query?
Sir, comment chat box.
Okay, yes,
Can,
sure. So I will keep the
I'll read
chat.
only one question. Inderjit sir has asked, sir,
Can
show
show
a
a passive capacitor
passive
in
capacitor.
layout. Yes, you can do passive capacitor in layout also. So if you want to do that, okay, let me create a new cell, and then I will do capacitance and then layout. Then okay, so I have got this window. Now I will go to components. So here I have the options. I can have poly 1, poly 2 capacitor, or I can, is there any other option? Let me see, because I have not laid out poly capacitor. So it seems that I have only one option for laying out capacitor. Poly 1, poly 2 means it's a 2 poly process. So when you go here, so something got attached to my mouse, so I place it here. Then you can see that, okay, so let me show you a 3D view of this. So let me go and see the 3D view of this. So here we can see the 3D view. So can you see the 3D view, dear Indrajit? So you can see that this
Yes,
means
sir.
this represents one polysilicon layer, and this yellow thing that represents second polysilicon layer, right? And then this dark thing that you are seeing, that is representing a dielectric, right? So you have one plate of the capacitor and you have bottom plate of the capacitor. Of course, the bottom plate of the capacitor is much larger, so that is there to make connections. So actually the area of the capacitor will be governed by the area of this top plate, and then you have this metal on the top plate to make the connections. So is that clear? And then we will do the connections, but is that clear?
Yes, sir. Yes, sir.
So 3D view actually helps us in seeing it clearly. So after that, what we can do, actually, we can make connections. So we need to take out two terminals. So we can do left click here and let me do right click here. So you can see you got a metal line, right? Similarly, for making connection with the polysilicon, what we can do, we can actually bring this polysilicon connection between metal and polysilicon. No, not metal. I need to do a connection with polysilicon. Oh, it's speaking. So, okay, let me. When this happens, what is happening with me? It is happening because here this is metal line is selected. You see. So this can happen with you also. Why it is happening? Because you see that here this metal line is selected. So when it happens with you, you go and select the appropriate layer. So I select polysilicon now. Sorry, I select this. Yes, I select poly, and then I go here, left click and right click. So now you can see that I have made a connection with this polysilicon and metal. So I have got this connection, and this has got some misaligned. Okay, let me run the DRC 5. So it is full of DRC. Let me see what DRC it is. So okay, it is actually this is violating the poly spacing. That is the DRC error. So what actually I can do? I can let me zoom in. Let me zoom in. What actually I can do? I can actually bring it. Why I am seeing this? I think something two layers got attached. Let me bring it again. So I make this connection, and then what I can do actually, I can shift it here. Shift it here. I think I can do this. Let me do DRC. It's full of errors. Whatever. It is not connected actually. I think I brought it, but it is not connected. So it is not connected actually. So let me first make a connection, and then I shall move it. Okay, let us move it like this only. Let me run DRC again. Right, so now I am not getting any error. So you can see that now I am not getting any error, right? So this way, and now you can actually take a metal contact. So I select here, and then I can bring the metal line out. So you can actually adjust it. So now you have got the two terminals. If this metal line is wide, so what I can do, I can select a pin here. Okay, I can select a pin here, and then I can connect a metal. So this way you can get a capacitor. Is that okay?
Yes, sir. Fine.
And then you can go and change the properties by double clicking on it, and you can change the properties, means what shall be the size. Okay, and then you can put the value of the capacitor. So again, when you have to decide upon the size of the capacitor, you will have to go to technology file. You will have to go to technology file, and from there you will have to see what is the capacitor. So here I don't see, yeah, here I see, here I don't see a poly value. Means you will have to get those values, from looking into the technology file. So that is actually what you will have to do. And on the other hand, if you are using commercial tool where you have the PDK attached with your project, so these informations will actually be available. That will be implicit. Any other query? So I think there is no other query, that was sir.
मुझे भी ऐसे लगता है. Let us. Anybody wants to ask anything? I don't think so. Okay. Sneha madam.
Hello, sir.
हाँ.
Hello, sir.
Yeah.
Sir, today morning. Hello.
Yes, please.
Today morning one assignment is given, sir. That is of OTA, operational transconductance amplifier.
Okay, ma'am.
So it is, I think, from the book Allen and Holberg.
Okay.
Huh. So shall we go for designing it in schematic in electric and then simulate in LT-SPICE?
Of course, ma'am, you can do that.
The dimensions are, sir, M1, M2, 13 by 1, 13 by 1. And M3, M4, they are around 15 by 1 and 15 by 1. Like that they are.
So I think that 15 is micrometer and 1 is micrometer.
Yeah, yes, sir, it is micrometer.
So yes, you can go ahead and use electric to do the layout.
Okay, sir. Okay, okay. Thank you.
See, that length 1 micrometer does not mean that you are using 1 micron technology. It could be 0.35 micron also. It could be 0.18 micron technology also. So it will be given in the book which technology you have to use.
Okay.
So you can go ahead with that.
Thank you, sir.
So thank you, Naushad sir. Thank you very much. Uh, this is the last technical session, and still you you were engaging participants, and they are asking the questions. That means you're still active. Thank you. Thanks a lot.
It was my pleasure.
Yeah, and sir, this is, and it is really a difficult task, very very difficult task to demonstrate the layout, and you were doing on fly. In fact, I have seen the people, they simply open the stored files in earlier previous sessions also. Whatever they had already created, those layouts they were opening and showing the examples. And you started from the scratch and you have actually built the entire layout. It was really great. On-fly demonstration of layout is not a simple task, and solving all those layers. So thank you very much. And this is a virtual memento from our side. Please accept it.
Yeah, it's my pleasure, Professor Rathore. And I actually tried to feel confidence in the participants, and most of the participants, they are teachers, and many of them may not be having a commercial tool like Cadence and Mentor Graphics with them. So I tried to convince them that even though commercial tool is not available with them, they can go ahead and teach their students or instill that layouts which they can teach their students. So means this is a very good
Yes,
thing.
yes, yes. Exactly. So we should not be dependent on tool completely. Otherwise, we become handicapped. So
Yes.
yes. So if our fundamentals are clear, anything can be done. So thank you, sir. Thank you very
And
much
it was
for
my
this.
pleasure to interact with the participants.
Yes.
So I thank the organizers, especially Professor Rathore, for giving me this opportunity to interact with the participants. And I also thank all the participants for showing their interest, because after my demonstration sessions, I used to get emails from the participants asking for some query, asking for some file. So that actually showed that many of the I was able to get many of the participants interested in using this electric and LTS spice tools for the simulation. So I'm pleased with that. Thank you all. Thank you very
Yes,
much.
sir. Yes, sir. And files which Naushad sir has given, TSMC 180 nanometer, he has only given to me. I have uploaded on the Moodle. So you can see the Moodle files are already there. So your home assignment is like this. Whatever is has been taught in the morning, that two-step op-amp, you complete that design, and you can use these model files. If you want, you can use any other model file. It's your choice. But at least try something on LT Spice, and please submit it by tomorrow morning. And as usual, tomorrow we will have our quiz for 1 hour. But realizing the difficulties from the participants, what I will do is I will open the quiz at 9 and I will close the quiz at 11, and duration will be 1 hour. Okay, because sometimes it happens that people are not able to connect, then there will be an issue. So 2 hours gap I keep, complete 2 hours. Within that 2 hours, you can appear for 1 hour. But please understand that appearing for this assessment is compulsory from our side. Please, if you don't find the assessments, if you do not appear at all, then probably your name will not be there during the validatory session. Okay, so no certificate. Please, you'll have to make sure that you are appearing for this exam. Okay, because that's the final exam. And please do these submissions, and that's it. And tomorrow we have a very fantastic session planned for all of you. It is about fire safety and security. We have a very good guest, so please attend at 2 p.m. and enjoy tomorrow's validatory session, 1.5 hour session or maximum 2 hour session. So 2 o'clock, please. I want all of you to be joining. Already there are so many candidates, and see how many are joining the sessions. So you please join. I can see these are the regular candidates. You must join tomorrow. Okay. So thank you very much. And morning session video also I'll try to upload because it got recorded in Cisco, even if it is not been live streamed, but it got recorded in Cisco. So I will upload that. And this anyway is live stream, so not an issue for this particular video. Okay. Thanks a lot. Anybody wants to ask anything?
So, okay, Rathod sir, I'm leaving.
Yes, sir. Thank you very much, sir. Thanks a lot.
Okay.
I'll get back to you afterwards. Okay. Thank you, sir. Thank you very much.
All of you take care and stay safe. Bye.
Yeah. Please.
अभी जो लैपटॉप पे यार